Hello students, so in this lecture we will discuss about mechanical alloying, and it is one of the synthesis routes to produce nanomaterials, and this is actually a top-down approach. So in mechanical alloying, or it's also called milling, and it was originally developed by Benjamin of International Nickel Company for the production of oxide of dispersion strengthened superalloys. It's called ODS. It's oxide of dispersion strengthened superalloys. Now, it is not widely used for the fabrication of nanocrystalline powders. So, nanocrystalline powders are being produced using this method. And recently, it has been also been used to make something called high entropy solid solutions or high entropy alloys. Come to it later on. Now first we will focus on this method of alloying of this mechanical alloying process. Let's concentrate on this. Now it is carried out in high energy mills such as vibratory mills. We have high energy vibratory mills, or it also carried out in planetary mills, and also actuator mills. So one is there are three ways by which you can make it. One is high energy vibratory mills, planetary mills, and actuator mills. So we will first take up one by one. So in vibratory mills, one has a wire. So we're discussing now vibratory mills, and we have a vial, it containing the sample and the grinding balls. Contains the sample and the grinding balls, and it vibrates in all the three directions. So vibration in is three-dimensional. Now, because of the amplitude about 50 millimeters and speed about 12 rpm, so it's the speed is 1200 rotations per minute, and amplitude is about 50 millimeters of the vibration, and the ball velocities are high. That is why it's called high energy mill. So we have a high ball velocity, and it is ordered of 5 meters per second, and the force on the ball's impact is unusually high. So this is the vibratory mill, so it causes a high force on the samples. The first one. The second one is the planetary mill. So in a planetary mill, the wheel rotates around their own axis. While rotates along its own axis. And also around the disk. So it's like a planetary motion. So that is why this name planetary comes into picture. It resembles the planetary motion around the sun. So what happens in this is that there is formation of centrifugal force, and that is produced by the wheels, produced by rotating the support disc to get the act on the barrel contents. And so this is the reason the grinding takes place. So now, since the vial and the supporting disc they are moving in opposite directions, the centrifugal force alternatively act in opposite directions. The centrifugal force also acts in opposite directions. And this is followed by material being ground and grinding balls being lifted off and traveling freely through the inner chamber of the vial, colliding against opposite inside vials. So grinding vials and balls are available in 8 different materials. They are made up of agate, then silicon nitride, Si3 and 4, sintered corundum, silicon carbide, zirconia, Zero2, chrome steel, chromium nickel steel, tungsten carbide, and plastic polyamide. So there are different materials of the grinding balls and vials. So now the third mechanical alloying process, that is called the attrited bone mill. It consists of a stationary vertical drum in which vertical shafts rotates with a series of horizontal impellers. Vertical shafts rotates with a series of horizontal impellers which are attached to it, and they are placed at right angles to each other, and the impellers through the rotation energize the ball charge, causing powder size reduction. So these impellers are important. So they energize the ball charge, causing powder size reduction, leading to powder size reduction. The defect of the walls, and this is due to impact between the walls and the container wall and between the walls. And particle size reduction also occurs partially by interparticle collisions or by ball sliding. Now, this mechanism of nanocrystallization during high energy ball milling was first proposed by H. Fetch in 1983. He summarized the phenomena of development of non-crystalline metal structure into three stages. So he called it as three stages. First is localization of deformation into shear bands with high dislocation density. First one. The second step was dislocation, annihilation, and recombination. Dislocation, annihilation, and recombination. To form nanometer scale subgrains, leading to nanometer scale subgrains. And the last stage was transformation of subgrain boundary structure to high angle grain boundary. So subgrain boundary to high angle boundary. So it's basically a self-organization into a random crystalline state. First there is localization or deformation into shear bands, then all sort of defect recombination into formation of subgrains is the main thing, and then subgrain transformation to high angle grain bond. These are three steps. During the high energy bond building, the powder particles are immediately flattened. So the samples or the powder particles which are being fed as samples, say powder particles, they are repeatedly flattened. Cold weld and fractured. And rewelded. So wherever a ball collides, some amount of powder is trapped in between them. So the impact from the ball causes plastic deformation of the powder particles. So we can call them as causing plastic deformation, and also accompanied by fracture in some cases. And work hardening also takes place. Another important aspect, as they get hardened, that is called work hardening. By work hardening means when we have too much dislocations in a certain place. So these too much dislocations will cause a hampering of movement of one dislocation through this, because there are a lot of stress being generated surrounding these dislocations. So it becomes difficult for another dislocation to actually overcome these stresses and get past through this. So this is known as work hardening. So also causes work hardening, and as I have told you, there is also a formation of fracture. So after fracture, the formation of new surfaces, and they are weld together again. So that is how this rebuilding comes into the picture. Now the minimum grain size obtained through high energy ball milling has been related to several physical properties. So I should say minimum grain size is actually a function of a lot of physical properties. Of the elemental metal, and the minimum grain size, let's call it as T min is inversely proportional to the melting temperature Tm. For low melting FCC metals. So this is one observation. Another observation is that for HCP, there's a different color here. For HCP, BCC, or as a matter of fact some FCC elements as well, with vented temperature above that of lead, that is 1555 degrees centigrade, that is of lead. For these elements, the minimum grain size is not related to the melting temperature of these materials, of these metals. So another observation was that this minimum grain size was found to be also inversely proportional to the bulk modulus E, and it had a relationship between the equilibrium distance between two edge dislocations and equilibrium distance between two edge dislocations. That means the higher is the dislocations, the higher will be the minimum grain size. Lower is the distance between two edge dislocations, lower will be the minimum grain size. There is a direct relationship. Now, research has also been focused on the validity of something called an Hall-Petch relation, which says that the yield strength is again inversely proportional to the grain size. And so Fetch represented a systematic report on the synthesis of non-crystalline metals by high energy ball milling, and so he ultimately concluded that the grain boundary energy of the ball mill nanocrystalline materials, of ball milled non-crystalline materials is higher than that of fully equilibrated grain boundaries.